All right, so up to this point, we've been talking about frequency response. We've been typically writing our function for specifically our transfer function of interest. So for us, it might have been V out over V in. We said it could also be I out over I in, but we've been typically writing this in terms of J omega, right? So or we can just, let me just do this. V out over V in terms of J omega. For us, it was 1 over 1 plus J omega RC for the RC circuit, right? So this is a function of J omega. Now I have this thing here that says S. What the heck is this S? Well, the S plane is something that we may or may not be familiar with. If you've heard of the Laplace transform, the S plane is directly related to the Laplace transform in that the S plane is basically a two-dimensional plane here. I'm going to draw it three-dimensionally, but it is a two-dimensional plane that has a real part, or a real axis, and an imaginary part. And the imaginary part is called the J omega axis, and the real part is called the sigma axis. And so the variable S is actually equal to sigma plus J omega. This is not particularly relevant to this class, but again, I like to give background for why I'm doing things and why engineers do the things that they do. And so the same way that we gave some background about why we use dBs, I want to give some background about why we use S in place of J omega, because the textbook sort of flippantly just says, oh, it's nice to use S instead of J omega for math purposes, but that's not actually what's happening at all. There's a reason why we can use S to replace J omega. I don't want it to be arbitrary. I want you to actually understand why we do the things that we do. So basically, all this is saying that I have written here is that I could rewrite my transfer function as a function of S rather than a function of J omega by simply saying S is equal to J omega. Okay, so in this case, I can just write that V out over V in of S is equal to 1 over 1 plus SRC. That's easy. This is actually even easier to work with because now I don't even have to think about J, right? That's the whole point of doing this. And the textbook will just leave it there, but I want to make a quick note of why we can do that and what is this S that we're even talking about. Well, S, like I said, is a complex variable. It's sigma plus J omega. And what S is used for is it's used to describe the general behavior of systems. It's used to describe the oscillatory behavior of systems, right? The sinusoidal responses, which is what we're looking at. And it's also used to describe growth and decay and stability of systems. So if a signal is decaying, like an RC circuit does, an RC circuit has some sort of exponential decay. It has some sigma in the S domain. And if it's oscillating, it has some J omega in the S domain. And so we know that all the systems that we care about right now, what we've been talking about, right? If I go back, you know what, it might be easier for me to just go back like this. I keep going back if I go back to here, what we're talking about is at different frequency values, right? There are different amplitudes. This is my input signal this whole time, and my red signal kept changing amplitude as I changed the frequency. That is me shifting the frequency that we're looking at and then analyzing what happens to the magnitude and the phase of this transfer function of interest that we've been talking about. So if I go back to where we are here with this S plane, let me draw a third dimension here, right? If I have S, which is equal to sigma plus J omega, let's say I just let J omega equal 0. I just let sigma equal 0. If I let sigma equal 0, right, S is equal to sigma plus J omega, and sigma is equal to 0, then I just get S is equal to J omega, which is what I just said that I could do here for frequency response. And so what this is if I just take the slice of this plot, this three-dimensional plot that I've drawn, if I just take the slice of the point where this is positive values of sigma, this would be negative values of sigma, this particular plane right here, right? I'm basically looking at a three-dimensional plane here that just slices through this volume. that plane or that particular axis, the j omega axis, that is my frequency response. It's the S plane, assuming sigma is 0. It's not any sigma in the positive direction, any sigma in the negative direction. It's just this axis here. So that's why when we draw it in 2 dimensions, and we have j omega here. Well, normally we replace this with F, because all we care about is the frequency in hertz. We don't typically look at things in terms of radians per second, but that's just as simple as omega equals 2 pi f, right? And so the other thing is that we really only look at this quadrant here, right? We don't even really look at negative frequencies. We only look at positive frequencies. So really all we care about is this portion right here. And so in the S plane, you know, this is all, again, just precursor to what we're doing. The next slide, I'm going to talk about poles and zeros, which I haven't talked about yet. The whole key here is that in the S plane, functions like this one have poles and zeros. What is a pole? So in this case, if I let S equal to negative 1 over RC, what is going to happen to this function, right? Well, if this is negative 1 over RC and I multiply that by RC, negative 1 over RC times RC gives me negative 1. And in the denominator, I'd get 1 minus 1, which is 0, right? This function would blow up to infinity at S equals negative 1 over RC. And so if I look at my S plane and I come out here to some point on this sigma axis, where sigma is equal to negative 1 over RC, I would get this explosion in this transfer function, right? What I'm plotting here, it would be V out of S over V in of S. And so my x-axis and my y-axis are the sigma and j omega, and then my z-axis here, right, this vertical axis is actually just the value of my transfer function for all values of S. So at a value of S equals negative 1 over RC, I'm purely real, right? I'm at a value of negative 1 over RC. I would get this thing called a pole. Let me actually move this closer just to make my point even clearer. I'm going to move it closer to the j omega axis. If I draw what happens here, it's going to be this giant explosion up to infinity of the transfer function. This is like a volume. I'm sketching a volume here of what's happening. And so this volume is going to kind of look like, I don't know how to describe it, maybe like the handle of a baseball bat. It's starting to like mound here. It's mounding. And then it's blowing up at a value right here of negative 1 over RC. The value is infinite, right? So this would just go exploding off in the z direction to infinity. And so what we're looking at when we look at the frequency response is we're actually looking at a slice of this plot, right? It might be just this slice right here, but then going down into the j omega axis, we're getting something that looks like this. I'm just looking at a slice. If I were to take a slice of that volume, I guess it would make more sense if I drew it like this. Right? So I'm taking a slice, and then if I were to come over here, like I said, and just look at this quadrant right here, what I would see is something that looks sort of like this. And that's exactly what we saw when we looked at the magnitude of V out over V in for the RC circuit, right? And so this is all background knowledge, again, just to let you know why we're doing what we're doing. But it is important to note that S can be used to replace j omega when we're talking about frequency response, because we're basically looking at this giant S-plane plot that has all this other stuff going on, but we're assuming sigma equals 0. So we're only looking at this axis, which is the frequency response that we've been talking about this whole time, okay? So from now on, we're going to be looking at these transfer functions, and we're going to be putting them in the S domain. We don't need to worry about this plot at all. Again, all we need to worry about are these plots, the Bode plots. But I want you to know that the reason why we can replace S with j omega or j omega with S is because what we're really looking at is a slice of this plot where sigma is 0. Okay, so this video has probably gotten really long, probably gotten really confusing. Forgive me if it's really confusing. the main takeaway is that we can replace j omega with s and make our lives easier. And we're going to be looking at poles, and we're going to be looking at zeros, and all of that stuff is relevant to the frequency response, but it's relevant because it's also relevant to this S-plane plot. So just so you know what's going on in the background. But if you just want to take one thing away from this slide, it's that we can replace S with j omega or j omega with S when we are doing frequency response. Okay, so let me go ahead and end this video before I confuse anybody any further. And in the next video, I'm going to start explaining what poles and zeros are.